Okay, hi everybody, and welcome again to Bay Vision Virtual Meetup, AI in Medical Imaging. As always, it's great to have this wide audience from the medical device and AI communities, not only from the Bay Area, but from all over. This webinar is going to be recorded. You'll get a link afterwards to the video, and you'll be able to write in your questions for the speaker, which we'll review at the end of the webinar. My name is Moshe Safran. I head up RSIP Vision USA. Just a few words about us before we get started. We're an AI solutions company. We're focused on building computer vision capabilities for medical imaging applications, and we partner with the medical device industry to help them develop new technologies and take those technologies from R&D all the way to production. And our teams work across multiple medical domains and imaging modalities: cardio, ortho, gastro, surgical navigation, surgical robotics. And we're actually heavily involved in the endoscopic and surgical imaging space. There's really a ton of activity in the industry these days in computer vision and we can call AI assist in general, image segmentation to 3D reconstruction, workflow analysis, motion estimation, detection of surgical instruments. There's really a very wide range of use cases that we're seeing in our experience and applications that are opening up to the wealth of data that's coming out of present-day medical procedures and the OR, and of course, recent advances, which is already, you could say it's already old news, though, all the recent advances in AI and computer vision, but of course, the field is showing no signs of stopping. And as such, I am more than delighted to introduce our guest speaker. Today we'll be hosting Stefanie Speidel, Professor for Translational Surgical Oncology at the National Center for Tumor Diseases in Dresden. Early this year, Stefanie organized the Endoscopic Vision Challenge at MICCAI 2020, which was very interesting for us to read about as well, and very relevant. Our speaker will introduce today surgical data science as an emerging scientific discipline and enabler for AI-assisted surgery, including several examples how to optimize individual patient therapy by turning available data into useful information. A focus of today's talk is going to be soft tissue registration and workflow analysis for context-aware assistance, as well as data generation, artificial data generation for machine learning applications, and finally, remaining challenges and strategies to overcome them. Again, please feel free to write in your questions, and we'll try to review as many of them as we can towards the end. So, Stefanie, thank you again for joining us today, and I will pass the floor over to you. Okay, just a minute.
Yeah, thanks a lot for the invitation. I'm happy to speak today to you. So I'll share my screen now. So hopefully, can you see my slides now?
Yeah, I can see it. It's good.
Okay, so perfect. Again, thanks for the invitation. I'm happy to give this webinar today about AI-assisted surgery. And I'm located in Dresden at the National Center for Tumor Diseases. You can see here on the top right side our new building, which was officially opened 3 months ago, and it includes an experimental OR and a simulation room, everything focused to AI-assisted surgery, where we intensively collaborate with the surgical, the clinicians on the university clinic campus. So our group, the expertise is computer and robotic assisted surgery. And I will now show you some examples on research we are working on. So I want to start with an overview. So we hear a lot about AI success story in medical image processing, but what about surgery? So you can see here some popular examples. So many algorithms that were published that can diagnose, for example, pneumonia better than radiologists, or for a method for skin cancer classification, or for breast cancer. And they have all in common that they were trained on a large set of images. So I think there were over 100,000 images that were used. And so here is one of the main challenges in surgery. And I will now introduce these challenges. So I will start with the term surgical data science and give a definition about that. And so let me start first with some numbers you might not be aware of. So according to a recent Lancet comment, post-operative complications are the third most contributor to death worldwide. So there are a lot of studies which estimate 9 million post-operative complications annually. And surgery involves a lot of skills. So it's a teamwork. So you have to work as a team. You have to do fast decision making. You have to have a certain kind of situation awareness. It's a really dynamic environment, and you also have to have leadership qualities. And it's not surprising that the outcome depends a lot on the experience of the surgical staff. So you can see here a study which relates hospital volume and surgical mortality for 2 cancer surgeries, which are quite complex. And I mean, it's not surprisingly that the mortality decreases if the hospital volume increases. So the outcome depends heavily on the experience. So this leads me to the term surgical data science. So the initiative was founded in 2016 with my co-chairs Lena Meyer-Hein and Pierre Janel, but there are also a lot of international experts involved, and the objective is to improve the quality of interventional healthcare by capturing, organizing, analyzing, and modeling of data. So, and here is one of the major bottlenecks in surgery, the data aspect. And for training our methods, I mean, you all know that we need a lot of data, but this data also has to be annotated. And if you compare it to a medical image processing, you have in a procedure. Surgery is a procedural process where a lot of people are involved in a dynamic environment, and complex operations, they last for several hours. And imagine you have to annotate this data. So here you can see a modern operating theater, which involves a lot of different medical devices, materials and instruments. We have robotic systems or navigation systems, anesthesia data. And our vision is that we don't have these single devices anymore, but a sensor connected environment where we can analyze the data in real time and provide the right assistance at the right time. So our system perceives the data, it does a situation interpretation, and depending on the phase of the operation, a real-time assistance. So that's our vision of a modern operating theater or a modern AI assistance in surgery. So I will now give you some examples on such topics we are working on, starting with data generation. I mean, I already mentioned that this is one of the major bottlenecks we are facing. Then I'll show you an example of advanced sensing. And I will focus a bit more on soft tissue registration or data fusion in that sense. Then we will see something in the context of context-aware assistance. And in the end, I also want to show you something in the, about surgical training, because all these methods I will show you can also be applied to surgical training settings. So I will start now with data generation, and an important challenge for evaluation and benchmarking all of these AI algorithms is the lack of large training data sets. So generating realistic looking computer simulations where we exactly know the ground truth instead of having an expert manually label the data would be really important. So, but up to now, models which are generated from the topics.
Yes, now we're back to topics. Okay, yeah, I think we're good to go. There are even more attendees now than there were 5 minutes ago because some people dialed in.
Sorry, I hope the connection is stable right now. So I continue with the data generation. So we use the unpaired image-to-image translation to generate realistic synthetic data. And this is possible even if the data is unpaired. So we don't know the direct mapping between samples in one domain to samples in the other domain. So, and if we put additionally a certain kind of loss, it also enables us to control the style of the translation result. So in the end, we have the increased diversity in the data set, so different textures and so on. So the data is and code is available. So if you're working in this field, this might be an interesting data set. We have over 20,000 input images, and you can translate them into different styles. And we also have labels for segmentation or depth if you're working in 3D reconstruction and so on. So the next topic I want to show you is in the context of advanced sensing. And this is a work from a group in Heidelberg we are closely collaborating with. It's Lena Meyer's Hagen group, and they developed a new multispectral image analysis endoscope, which involves deep learning to do multispectral image analysis. So you see here a conventional device, and this is a multispectral prototype. And it uses deep learning to estimate the tissue properties. So you see here a clamp that is attached to a renal artery, and you see here the blood volume fraction. And if the clamp is applied, the blood volume decreases. You can see this with this new type of endoscope and the algorithm behind it. And if you release the clamp again, then you see that the oxygenation is increasing. So this was an example of advanced sensing. And my next example is in the context of data fusion. So we are working intensively in the area of soft tissue registration. So the challenge here is that you have pre-operative data. You can generate out based on this a 3D model. Here you see a 3D model of the liver with a tumor in yellow. And but if you want to use this in an intraoperative setting, this is a typical view in liver surgery. You have right now to fuse this data mentally. So what we are working on is providing an augmented reality visualization. And this is quite challenging because the liver is deforming a lot. And we also want to predict the deformation in real time to adapt the visualization accordingly. So here you can see a typical scene in laparoscopic liver surgery. So you see the data is extremely noisy. We only have sparse correspondences. And what we see is not what is behind the tissue. So we have unseen boundaries and unknown boundary conditions. So typically, you can use a finite element method, but this is really difficult to parameterize and to parallelize, and it's also difficult to deal with unknown boundaries. So we also have very sparse literature regarding the boundary conditions in that setting. So a possible solution, we thought we can learn the tissue deformation and also learn to match the surfaces so that we get rid of the correspondence problem. And we developed a data-driven biomechanical model. So the idea here is that you reconstruct the surface based on the stereo laparoscope. We have, for example, from the Da Vinci surgical system. And we have the geometry from the preoperative model. And then we feed this in our volume to surface registration network. And what we get out of it is the displacement field in real time. So we can register the surface and the preoperative model. And it works directly on the geometry. So we don't have to solve the correspondence problem. And what's also important to know is that it trains on random simulations. So again, we use synthetic simulations and adapted it to a real problem in surgery. And we don't have to feed in if we have a new patient, the geometry of the patient, because it adapts directly to new patient geometry based only on these random simulations. So we generated random meshes and simulated random deformations, also random boundary conditions, using the FEM simulation. And then we extracted a partial surface of the deformed mesh, which acts as an intraoperative partial organ surface. What we reconstruct from the surface we see from the laparoscope. So to pass this data to our network, we encode the geometry as distance fields. So you can see this here on the left. And the displacement field is also expected. And the distance fields are the input to our network. And the displacement field you see here at the bottom is the output. And so the target, what the network should predict. And this whole process is repeated for 80,000 meshes to make our data set for the soft tissue registration. So we did a lot of experiments. So we looked at in silico data to see if the prediction is usually plausible. So we estimated that we see approximately 20% of the partial surface and feeded it into a network, and in general it works quite well. But here you can see also cases where it doesn't work. So for example, if we have a really big deformation, or if we only see a small portion of the surface, so we need at least 20%. So we also did experiments in human CT breathing motion, and here we see that we can reduce the displacement error to 5.7 millimeters approximately. And in laparoscopy, we don't have the ground truth here, but we showed that it worked qualitatively on the data. So we are still working on this. So open issues are, for example, a large amount of noise and changes in topology. So for example, if someone is cutting. Okay, so as I said, we reconstruct the intraoperative model based on the stereo images, and this is a standard stereo reconstruction approach we use here. And then here you can see the result. This is the result of our stitching. We used here a SLAM approach to segmented the liver in the endoscopic view before to get the surface model we used for our registration network. So the next part I want to show you is context-aware assistance. As I said, our vision is to provide the right assistance at the right time. And therefore, we need to know in which phase the operation is. So you can see here an example where we analyze the video stream. We use the Bayesian neural network here to estimate the remaining time of the surgery. And therefore, we detect the phase. Yes, we use this approach for remaining time prediction. So our vision here is not to use it only for remaining time prediction, but also to use it to predict complications, for example. But therefore, we need a lot more training data we don't have right now, but we are working on it. And a next example is anticipation of tasks for surgical assistance. So for example, for human machine cooperation, we need to know what the next task will be. And we looked at anticipation of surgical instruments from video data. So we formulated it as a joint regression and classification task, and we predicted the time until a certain instrument occurs in a defined time horizon. So compared to general action anticipation in computer vision, our method is more applicable to surgical scenarios. So we don't make assumptions about the timing of actions. And for training, we only require labels for events we want to anticipate. And for the inference, we only need raw video data. So here we used a Bayesian deep learning framework to also account for uncertainty with future events. And we showed that we can identify events which trigger the usage of instruments through uncertainty quantification. So for example, using the scissor could show that the network identifies the placing of clips as a trigger for cutting. And so this anticipation, we are still working on it. So we want to explore also more focused on the task formulation, and therefore also the code is available if you're working on anticipation tasks. So next, I want to focus a bit more on surgical training. So because all the methods I showed you can also be applied to training tasks. And normally, if a novice is trained in laparoscopic surgery, there are these kind of box trainers or virtual trainers they can use. If they use a box trainer, normally a more experienced surgeon is giving them feedback. And as you might imagine, this does not scale. And we thought, okay, can we do a data-driven surgical training approach where we, for example, incorporate different kinds of sensor to capture the performance of novices, intermediate, and expert surgeon, and also how can we provide a meaningful feedback to improve the learning curve. So here you can see an example of our training setup. So we have 4 different tasks we are looking at here at the medical courses in Dresden. So we collect data from trainees and experts and do a computer vision-based scene and skill analysis. So in the end, we want to estimate how good is the performance. And we also want to learn to estimate the score on a scale of 1, which is a very poor score, to 5, which is very good. And these are standard scores that are used in surgical training. So for example, GEARS or OSATs. And to do that, we decided to use a 3D CNN approach. So, so contrary to common 2D CNNs, they can be used to extract features along the spatio-temporal dimension. So our goal is here to predict the skill and level and the class of the participant. But the drawback of 3D CNNs is that they can only produce or classify a small number of video frames. So only snippets can be classified. So as you can see here in the example, the task is to predict, is this an expert, intermediate, or novice with performing this. So our idea was to split the video into smaller snippets and then to classify each snippet individually. And if we do this, we can then aggregate the results in the end, and we then know the skill label for the whole video if we aggregate the classification results of the snippets, which were put through our 3D CNN. So now the question is how to train this 3D CNN. So basically, you would put the video snippet through the 3D CNN and compare the obtained class scores with a ground truth, and then backpropagate the error. However, we only have here 1 label per video, and we don't have a label for every single video snippet. So we are dealing with a sort of weakly labeled scenario here. Of course, we could assume that the label of the snippet is the same as the label of the enclosing video. However, just because a video comes from a beginner, it doesn't mean that every single snippet in the video is performed in a bad way. So there may be a certain overlap with expert performances. And to get around this, we extended the 3D CNN into a temporal segment network. So now we look at several video snippets and we use a Siamese architecture to classify all of the video snippets at once. And then we can predict the skill label. So these are some examples I showed you for AI-assisted surgery. And in the end, I want to wrap up some remaining challenges, and there are still a lot of challenges to solve. So first of all, I mean, I talked about data, and this is still one of the major bottlenecks. So we need annotated data, and annotations are quite cumbersome to get. You need an expert to label them. So, and the data has to be representative. So as I said, we want to predict complications, but therefore we also need data where we have complications. And the data generation, I mean, there are different strategies, for example, crowdsourcing or self-supervised learning or generation of synthetic data. So there are still a lot of research problems to tackle. Another challenge are the methods. So in surgery or in medical applications in general right now, deep learning methods are a black box. And so for medical applications, it would be better if the result is correlated with some uncertainty or is reasonable. So, I mean, there is a lot going on in the AI, explainable AI topics, which I think is also an interesting thread of research for medical applications. Then medical devices is another challenge. I showed you my vision of this future OR, but therefore we also have to get access to the devices, and we also need standard interfaces and so on. And the devices have to be integrated and connected in the OR. And then in the end, integration is also a challenge because an assistant system will never be used if it's not integrated in the surgical workflow. So I think context-aware assistance is also a really important challenge we have to solve. So in the end, my vision of the OR of the future is a sensor-connected environment where we can analyze in real time the data and to provide the right assistance at the right time. For example, context-aware visualization, or remaining time prediction, or even complication prediction. Or if you have a robotic system, you can also imagine, for example, an automatic camera guidance system. And then in the end, I also want to draw your attention to the endoscopic vision challenge. If you're working in this field, this might be a good site for data sets. We are doing this since 2015 together with my co-chairs and all the sub-challenge organizers. We always have really cool challenges and with really interesting data sets, and most of them are publicly available. If not, you can also write an email to the sub-challenge organizer to give you access. So this is my last slide. I want to thank my team, my PhDs and postdocs in Dresden, my cooperation partners, and my funding agencies. Thanks a lot for your attention, and I'm open for discussions. And sorry again for the small gap in between to network problems on my side.
Thank you very much, Stefanie. It was a really fascinating talk. I know that I have a whole bunch of questions. I'd like to thank our audience as well. Please, I'd like to invite everybody to feel free to write in their questions. On the topic of explainability, so for instance, for a task such as the performance assessment task, like the gears task, do you think it might be beneficial in that kind of task to incorporate some sort of additional task beyond the, so it sounds like right now you're doing sort of a kind of black box classification. Do you think it's helpful in those situations to add something like pose estimation or tracking the tools to add an additional task to the network in order both to gain explainability and also perhaps to improve the classification performance?
Yeah, I think so. I mean, I showed you this video where we analyzed the scene, and we try to use this in addition to the 3D CNN I showed you to classify the performance. I mean, right now data is a problem. I mean, we recorded really a lot of data from novices. We have every semester there is a course in Dresden, and with really beginners, and we record them 4 times in this course. So it might be that we also see an advance during the course, but it's really difficult to get enough expert data. I mean, we recorded a lot of experts in Dresden, but I think this is not enough. We also need to go to other centers and get experts there. And I think it's also an interesting question if the experts are performing the task in a similar way. Because it might be that an expert in another center, because they have another way of doing this task, are doing it completely different. I think this would be also an interesting research question to look at.
Yeah, so I would think that the more variability you find there is between the experts, the more data you're going to need. That's just going to make the expert data collection even more expensive. Not to mention the issue of ground truth. So, yeah, one of my first takeaways from this talk is that I'm becoming more and more convinced that we're really going to need this simulated data in order to, to get to move forward in this space. Well, unless in the end there's just going to be one company like Intuitive, or that somebody gets their hands on this huge data collection operation and data annotation operation, but it just sounds like a huge operational challenge even for the strongest players to collect. It's the one thing to get enough data, but also to get the ground truth for that data generated is just it sounds like it's a huge hurdle here. I've got lots. Actually, you put in those 4 steps in the pipeline. Most of my questions are on the methods side. I'm really curious to read all these papers now. So like the soft tissue registration example for the liver, you mentioned that you're training the data on random simulations, right? Sort of random instances of the liver. Are you using some kind of model or constraints on those deformations? I mean, how are you defining the space of possible livers on which to train your network?
Actually, in our first approach, we didn't even use livers. We used organ-like meshes. And then we augmented the data with real livers, and we got an improvement in accuracy. But most of the data we have in our database are organ-like meshes. And we used a material model. I mean, we used an FEM simulation to generate the data. So we used a standard material model, nothing fancy with viscoelastic behavior, for example. And we, we tried to reduce, for example, the deformation to a certain kind of degree in the translation and so on. So the deformation still has to be kind of realistic. So I showed you also an example of our evaluation where it did not work in the in silico data because the rotation was too large in the end, and we all only had a small portion of the surface which we assumed was visible. Another problem is that the liver has 2 lobes, and in the CT data you don't see this. These 2 lobes, so there is a gap between the left and the right lobe, and actually, this change in topology is quite challenging for us right now. So we are trying to increase our database, incorporating such data where we have changes in topologies, for example.
Nice. There's a question actually now from Yuan. Can the deformable tissue model be applied in real time? So he already wants to use it in real time.
Yeah. I mean, this was our one of our motivations to use a CNN, because
Yes.
FEM simulations can be quite accurate, but there are really, I mean, regarding the performance, it's better to have a CNN, and I think we have like 50 frames per second, which we can process with the CNN.
Yeah, so that's another advantage besides the robustness. Basically, almost any CNN-based solution, if today prediction is not real time, then tomorrow it will be real time, right? Because in a year from now, the GPU is going to be, 2 times bigger than it is today, and it scales, I think, very, very nicely. By the way, for stereo reconstruction, you showed that you were, it was sort of an intermediate stage in that project. You're just using classical methods. Do you think like SLAM classical methods are going to be good enough for the surgical setting for stereo reconstruction, or do you think we're going to need deep learning? Because there are people who are doing supervised learning for this, trying to train networks specifically on surgical data. How necessary do you think this is, or from your experience, is the classical approach good enough?
Yeah, I mean, it depends. I mean, for I mean, we are testing different approaches right now. For example, we're using OrbSLAM, but one of my PhDs is also looking in a deep learning based approach, which are published recently. So the problem here is that I mean, we don't have ground truth data from a real operation. So so we cannot test it on real data. So we have like a phantom setup where we have a liver which we deform with mechanical devices and during a CT in the same time. So but still, I think it's a bit limited because it doesn't look realistic, and so the feature tracking, I mean, on the liver can be quite challenging because it's really homogeneous and
no texture.
Specularities, for example, but still in the phantom setup, we get quite good results with a classical approach. But I'm curious how the deep learning approaches are performing, but I cannot say something because we don't have results yet. I mean, there in this whole pipeline, there are a lot of error sources involved, starting from camera calibration.
Yes.
The reconstruction can be quite noisy because in the real surgical settings, I mean, we ask our surgeons to do a scan on the liver before with the camera so that we can reconstruct our model. But I mean, this is a step that is okay for them, but still it's very specific because we ask them, and then you also have sometimes areas which are dark or there is low contrast, and the reconstruction there is quite noisy.
Yes. Another question from Oz, actually going back to the skill assessment level. Have you also used handmade feature engineering? And if so, have you identified surprising features in that regard, which are less trivial in order to measure skill?
No, we did not use handmade features. We used only the vision channel for classification, so we don't have, for example, the trajectories or any other sensor input. And for that, we thought that a 3D CNN approach might be performing well. And I mean, we used the Jigsaw data set for that paper, for example. It's a public data set, and it's the only one in surgical training which is publicly available, but it's not a big data set. So it's difficult to draw a conclusion which method performs best because there is not enough data. I mean, we are working towards publishing a bigger data set from the recordings I mentioned in the talk, but still we have to see. So we did not use classical approaches.
Okay, so thank you very much again, Stefanie. Again, this recording will be available, so you can all share it with your friends, with those who registered and didn't get a chance to participate. As you can see, I think up on my screen, we have our monthly newsletter, Computer Vision News. I think Professor Speidel also interviewed for that a few months back. We have actually, this is pretty rare, but we've got another webinar of RSIP Vision going on tomorrow, this time our lead radiologist, to talk a bit about more our development process. Yeah, thanks again for joining at this evening hour, Dr. Speidel, and we'll be in touch. Have a good day and evening to everybody.
Thanks.
Bye for now.
Bye.
Bye-bye.